All right, good morning, everyone. My name is Vasmi, and I'm from VMware. And we'll be talking about OVS performance. I think this is good follow-on to the vSperf talk, which we just heard, and I will be showing some numbers. So we wanted to share the methodology that we have been using for measuring OVS performance and some of the learnings that we have collected along the way. And as I said, we'll present some numbers for different topologies. So we have been looking at performance in like different layers. So what we call the bridge layer would be just focusing on OVS performance for forwarding. And then a higher layer would be like an application layer where OVS is a component in a virtual network. We will talk about our framework and some of the configuration settings which we use. And lastly, we'll present some results and we can talk about that. So just want to point out that since OVS is unlike a hardware switch, the performance of OVS is dependent on where it's running. So it's not enough to say that OVS can do n packets per second without also talking about what kind of CPU you use and how many cores and so on. So this is just a partial list of some of the most important factors which affect what you would see as performance for OVS or any virtual switch for that matter. Obviously, for getting best performance, you would want to use a multi-core machine with fast CPUs. You want to make sure your BIOS settings are set to performance mode or the equivalent for your machine. Pneuma considerations are important. You would want the packet processing cores to be on the same Pneuma node as your physical NIC. We have seen significant decrease in performance if you're on a remote Pneuma node. The types of flows that are installed in OVS is important and can have a big effect. The type of traffic, whether it's TCP or UDP, the nature of the flows, and the NIC capability that are very important in the performance that you see in networking, obviously. So then things like the number of queues and whether RSS is supported, the various hardware offloads that the NIC supports for both native traffic and for the various tunnel traffics. And if you're doing application level performance, then the performance, the interface between the virtual machine, the vNIC, and OVS can be the dominant factor, more so than the virtual switch itself. Okay, talking about the bridge layer performance, which is the lower layer, we look at two simple topologies like this, the bare minimum topologies, to figure out like the best case performance in forwarding. So in topology 1 on the left, there's a single server with OVS installed, and packets coming into port 1 go out port 2 and vice versa. In topology 2, we have two servers, and here you can connect them using different kinds of tunneling and isolate the performance impact of different tunneling or overlay mechanisms, right? And you will note there are no VMs in these topologies. Okay. So these topologies can be useful for running RFC 2544 kind of tests. One thing which we found interesting was that if you use the default settings of test generators, then typically you may have to modify them for testing virtual switches, for testing OVS. So the way OVS works, as everyone knows here, is that if there's a miss in the kernel cache, packets are sent to user space, which then installs flows in the kernel cache so that all subsequent packets of that flow will take the fast path. So to prime the switches, what test generators usually do is have two phases, where the learning phase is send some traffic, which would prime the switches, prime the caches, and then they start sending test traffic, which actually does the measurement, right? With OVS, the kernel cache is actually flushed pretty quickly in the order of a second or two. And so In some of these test generators, the time between the learning phase and the test phase is longer than that. So you really don't get, you see the benefit of the learning phase. To get around problems like that, you can increase the max idle time using this vs kettle command. So that's something which we found out through experimenting. Okay, let's talk about a higher level. Again, we use a simple topology where we have VMs connected to the OVS on host 0, talking to VMs on host 1, and we use netperf as a micro benchmark where VM1 on host 0 talks to VM1 on host 1, and we can have multiple such pairs. And we run different kind of test suites to characterize performance. Let's. What I also want to mention that using these basic physical topologies, you can configure multiple logical topologies, obviously using different kinds of tunneling and overlay and different configurations. A word about the performance metrics that we usually collect. Obviously, throughput is important for stateful traffic, just Gbps for stateless traffic. Frames per second is an important metric. RFC 2544 talks about maximum loss-free frame rate, like 0 packet loss. For virtual switches like OVS, since there is resource sharing and your CPU may be doing other things as well, sometimes it's more realistic to aim for some small packet loss, right? So you can set a maximum loss threshold of say 0.01%, which is acceptable in some applications. It may not be acceptable if you're doing NFV for a telco, but so that's something you can play with. But of course, these numbers should be reported when you report your throughput. It's part of the methodology. Other metrics are connections per second. This is the maximum number of flows. Measure kind of indicates the flow setup rate in OVS. Latency, CPU utilization. It's important to measure to collect the utilization of all the cores on both the sender and the receiver side, and also report the utilization normalized by the gigabits per second. Measuring CPU utilization turns out to be not straightforward. We have found that tools like TOP, for example, often underreport the CPU utilization if the interrupt rate is high, which it is for networking traffic. So we use perf stat to actually count cycles using hardware counters, and then compute or derive the CPU utilization from that. And that's the command for perf stat. Also want to mention line rate. We know that, for example, for a 10 gigabit Ethernet, you can get a 14.88 million packets per second for 64 byte minimum size packets, right? But if you have that same 64 byte frame encapsulated in VXLAN, the maximum you can get actually just 9.06 million packets per second. And if you multiply that by 64, that's only 4.64 gigabits per second. So that's really the maximum you can expect if you're measuring things at a VM level. Just that's the theoretical maximum. So people understand that the max throughput is sort of decreased by the protocol overhead, but sometimes they're surprised by how much of the decrease it can be depending on what kind of overlays or protocols you're using. Performance number is not just a specific value, but often it's a range, and that's something which the methodology should account for. So for example, if things are normally distributed, maybe a mean and a standard deviation and other statistical things can be used, but often, say for throughput, things are not normally distributed. It's more likely to be within a range, uniformly distributed within a range, in which case maybe in the midpoint of the range and a tolerance around it would be more appropriate. So that's what we use actually in our tests. Let's go to our testing framework. So the goal is to automate everything 100%, use open source tools as much as possible, and sort of break the problem down into different pieces. So the different sub-problems that you want to do system setup and baselining, then upgrade the test components to the right version numbers and build numbers, and then set up the logical topologies, manage all the tests and execute the tests, and then lastly, collect reports and process the data, push it to a database, and so on. So these are the different sort of steps in any testing framework. So this is the solution that we've used, and so we use Ansible for doing the system setup and baselining, for upgrading test components, for setting up logical topologies, different Ansible playbooks for each of these, and for test management and execution, we have used a combination of Ansible and the nose framework of Python and Fabric. These are all standard Python packages. For report generation and saving results, we've used Django and Highchart. Since we use Ansible a lot, a little more about that. We chose it because it sort of has a nice architecture where in a playbook you specify the desired state of the system, and if the system is already in that state, Ansible checks. It won't make any changes. If it's not, it'll make just the required changes, and it'll tell you what it changed. So it's pretty efficient. That's the reason we picked it, and it already has packages to do a lot of the regular, the standard modules to install things, and some of the modules that we needed we developed, and we also contributed the modules to Ansible, and you can get them from the website. And it's all essentially Python, so it's pretty easy to develop and debug. And we found OVS is very automation friendly, just because of the way you can look at the state of the configuration and modify state and add and delete things. Create and delete objects. Okay, moving on to some results. So this is the system under test that we have. We have 2.6 16 core machine, and for the results I show, it's for OVS version 2.3.2, and we are talking about kernel OVS. So this is not DPDK. And we have an Intel NIC. So before that, the configuration of the VM and the host is obviously important, and they should be configured for high performance and also consistent performance. And there are guides available from say Red Hat or Canonical, good guides available to configure your system correctly. And so this is just an example of the configuration which we have used. I won't go through all of these, but for example, we disable IRQ balance. We found that results to be much more consistent if you disable IRQ balance and affinitize NIC queues to cores. Okay. So this is the same slide I had presented before. This is the topology for the bridge layer, and I'll show you some results that you get with these topologies. All right. So this is for the what we're calling the simple loopback case with OVS in one host. So as you can see, with one core, we get about 1 million frames per second on our system. With 8 cores, all on the same Pneuma node, we get about 6 million packets per second. And on our 16-core machine, we could get about 11.5 million packets per second. And on the right is the same data, but expressed as gigabits per second. And you can see it reaches line rate around, not for minimum size packets, but for slightly larger packets. Right. This is for the two server case, and actually the results are pretty much similar. For application-based testing, we use netperf, as I said. I'm just showing you that same slide again to remind you. So this, let's talk about, this slide has a lot of information, but I think it's interesting to see all of it. So on the left is the throughput, and that's what the bars represent. And on the right is actually the normalized CPU utilization for that throughput. And we have these, I don't know if you can see it well, but the orange dots represent the center side CPU utilization, and the blue dots represent the receiver side CPU utilization. So you can kind of see what the bottleneck is in this by looking at this one chart. And we have it for the VLAN topology, the STT topology, and the VXLAN topology. So for small size packets, usually it's the sender CPU bound. For VXLAN, in this case, the throughput is pretty low. That's the green bar. And the reason is because there's no hardware offload in our case. And so the CPU cost is pretty high. And that turns out to be the bottleneck for VXLAN. So all these slides are there on the conference website, so you can look at it later. Moving on, so the same test we repeat for 8 VM pairs, and so for example, you could look at if for a topology, if you've reached line rate, then you can look at the CPU utilization in this case and see that for STT, the CPU utilization is much lower than for VXLAN in this case, right? So let's see. Okay, I'll just skip over that. I'm running out of time. For testing with UDP, so that was with TCP traffic. For testing with UDP traffic, that's important because you can get frames per second and cycles per second. The caveat is that with UDP tests, if they result in significant packet drops, then that skews your numbers and it's hard to interpret. So use packet generators that can control the offload load so that you don't get too many packet drops, and that you avoid fragmentation of large datagrams. We use netperf TCP-RR. This is a good indication of the end-to-end latency, and here are some results for that. So this opens a persistent connection and does like a request response kind of test. For testing with multiple concurrent connections, netperf TCP-CRR is a good test. And so here we show the netperf TCP-CRR numbers with 1 VM and with 8 VMs. You can see it's about 26,000 CPS with 1 VM, and with 8 VMs, it's about 110,000 CPS. Connections per second. So it opens a connection and sends a byte and then closes down the connection. So that's all I have, and just to summarize, it's important to have a well-established framework and methodology and record all the various configurations and hardware and software details that you use for the test, and understand what the normal variations are and try to minimize them. And that's it, if there are any questions.
All right, let's thank our speaker. So if there are questions, we have some time. It looks like our mic is over on this side, so please come over here if you have a question. Go ahead.
Hi, Vasmi. You mentioned that you didn't test with DPDK. Do you have plans to test with DPK?
So we did not present DPDK numbers. We use the same framework and we have tested with DPDK, with SRIOV, with various things. So we do have numbers for those as well, and we use the same the methodology for testing the DPDK. We have done that. Yeah.
Sorry.
Yeah.
Do you have any quick results that you can share with us here? Are they similar to what you've presented here without DPDK, or?
I think Mariam could talk to that, but the DPDK can do line rate with minimum size packets, usually with one core.
So you talked about three things: CPU utilization, throughput, and latency. And you showed one diagram in which you had one VM talking to another VM. But none of the slides that you showed the individual VM performance, which is, and especially the speaker from the previous talk is here, where they were talking about NFV deployments in telco environments, where one VM could potentially hog a lot of resources. Being from VMware as you are, what is your way of testing the isolation that is needed for NFV to truly function well?
Okay. So
does my question make sense?
I'll try to restate what I understand, and maybe you
Okay.
can tell me. So I presented just a few topologies. So
Right.
one topology that I presented with the VMs is just VM being the endpoints.
Yeah.
So this is not the NFV case.
Yeah.
For an NFV case, we would have a user packet generator where packets going to OVS, which goes to a VM, which does some kind of a processing and forwards it back out. So that's a different kind of topology.
But you know what I'm talking about is performance isolation. When you're running, you were showing concurrency of CPS, connections per second, thousands of connections. But you're not showing how those connections are impacting each other's performance.
Yes. So I did not show that in this presentation, but usually in tests like that, we have noticed that the bottleneck is between the VM and the OVS. So, and that the vhost net process usually is 100% utilized. That's the bottleneck in that case.
Hi.
Hi.
Firstly, great presentation, and I'm delighted to see actually we reached several of the same conclusions in terms of testing methodologies. But one question I had was regarding the VM to VM tests that you were performing with netperf. One of our major considerations in vSperf is the accuracy of the tester, and particularly the timer on the guest and timing synchronization across multiple guests. So have you considered a topology where you're using your Spirent as an external traffic generator, bypassing some connection into your VM, and then doing your east-west type test and receiving your traffic again at your tester ultimately?
Yes.
And is that something you do within your framework, or?
Yes, so we have done that. I did not show it in this presentation, but we would have exactly that kind of topology where we chain through one VM versus chain through two VMs, chain through three VMs, and receive it finally at the Spirent.
Okay, and did you notice the big difference in performance across the netperf tests versus your external tester?
Yes, it's a different topology going through VMs. So the more VMs you go through, the more the chances of packet loss.
I agree, but my main concern is relevant to the accuracy of the tester and the results we're reflecting. One final question or comment. I didn't see anything about isolation of processes. So are you task setting any of your vSwitch processes or your VNF processes to cores, or are you using any of these methodologies to reduce any of the noise on the system in terms of testing?
Yes, in some cases we do pinning. I mean, it's a sort of a trade-off. We want to make sure our tests are reflective of real-world things where people don't pin. So we do tests like that, but for particular cases to reduce variations, we have run tests with pinning as well.
Okay, excellent. I actually think there's a great opportunity to collaborate going forward. So if you're interested in having a conversation on that later on, that'd be great.
Yes.
Thank you.
Happy to.
Let's thank our speaker one more time.